Good morning. Welcome to Krishna's class. We continue with our exploration of inner product spaces. And you recall the last lecture was on complex equation. Now we take up the discussion on diagonalization, which we have already seen in the context of non-inner product spaces. That is, vector spaces over a field F of finite dimension. In that case, we have even characterized such operators. So let us just briefly recall that, and then we can see, or we shall explore what further things that we could say about it in the context of inner product spaces. So once the inner products, the concept of inner products come in, so we will just see what advantages it gives and what more could be said about this. So let me start with this. So let me first explore the general theory that we have done in detail and then have a look at it. So you recall what we did earlier in the case of vector spaces of dimension whose dimension is finite over a field without any inner product structure induced on it. Okay. Let X be vector space over a field F and of dimension now we consider Lx. Lx denotes the space of all operators, linear operators X. Let T belong to Lx. Now we have seen that, recall this, we have seen that every ordered basis induces a isomorphism from X to F. Every ordered basis induces an isomorphism from X consequently what you have, see, corresponding to there exists a n by n matrix as a linear transformation on Fn induced by T and the isomorphism. See, the important point is that the isomorphism is not unique, because the choice of the ordered basis is not unique. Therefore, the isomorphism is not unique. Therefore, the matrix representation that you get for T is also not unique. We call that the choice of an ordered basis, or which you call a coordinate system. Is not unique. Is not unique. Consequently, there are many isomorphisms. Fn determined by this that means every ordered basis induces an isomorphism and vice versa. And vice versa. So this is a sort of an ordered basis, gives an isomorphism, and vice versa. Okay, the situation is like this. You have f v x, another copy of x. You have a linear transformation t. Now corresponding to t, see, so this is a copy of Fn, this is a copy of Fn, and suppose we introduce an ordered basis B, then corresponding to that there is a phi. Say this is x, dx, then there is this is an element of Fn, then there is the corresponding representation for Tx with respect to the basis B, and the connection between these two is given by the n by n matrix T with respect to B. This is an n by n matrix. With entries from F. Now what happens is this. See, if B prime is another isomorphism, and B prime is another ordered basis for x, then there is a corresponding isomorphism phi prime, and you have phi prime is an isomorphism from x onto Fn, which determines another. So this is actually x with B prime, this is Tx, B prime, they are in Fn, and you have another matrix T. So in general, Tb is not equal to Tb prime. Except in some specific cases, one case or two situations where they are the same is when we consider the zero operator. In that case, irrespective of what ordered basis you choose, it is the zero matrix that represents it, and then the identity operator, whose representation, matrix representation, is essentially the identity matrix, irrespective of what ordered basis you choose. Okay. So these are situations where they are equal. When they are the same, they do not depend on the ordered basis that you choose. But in general, this is not the case. Each matrix can be, so each operator And we have seen that it is not true that T can be represented by any n by n matrix. Any n by n matrix. There are some matrices which can be made use of, can represent a linear transformation, and there is automatically a relation between the different matrices that can represent the same linear transformation. In fact, the different that represent T are related through similarity a relation related that is there exists an invertible n by n matrix C such that this is something that you can easily see. Even from this figure you can find out how these two are related. It's quite easy to figure it out. Now you can you can see that connect these two. So in fact what you have is this Tx can be written as Tx equal to y inverse phi inverse this is equal to phi dB phi inverse. This is also equal to Tb prime phi prime phi inverse. It's simply the following, that is Tx is this we work it out in this way. First apply phi on x, you will reach here, and then apply TB, then apply phi inverse, you are at Tx. So equate the two, then okay, so I should write here x. X belonging to x. This implies phi inverse phi prime inverse phi prime, and consequently you see that this is just a quick review of whatever we did earlier. You can go back to my lectures on linear algebra, where all these things are discussed in detail. But I thought that may be worthwhile, before introducing what is called diagonalization, we have a look at the diagonalization problem in the case of a general n-dimensional vector space. Okay. Therefore, you have equal to, we will work this out. So you apply phi on this side and phi prime inverse on this side. So you have phi inverse. Now this you can put this in the bracket. Now you see this can be written as phi prime inverse. So you get phi prime, phi inverse when you work this, because they interchange. And you can see that, you can easily see that this is a map. See, start from here xb to xb prime. How do you get there? You first apply phi inverse, then you reach here, and then you apply phi prime. Or if you want to go from here to here, what happens is you first apply phi prime inverse and then apply this. Therefore, you see that phi prime inverse, phi prime inverse is essentially a map from Fn to Fn. By an n by n matrix C. Okay. Then C is invertible and C inverse is given by phi prime phi inverse. Okay, so this is invertible and it is given by this. So two representations representing matrices of T with respect to different ordered bases are related, and this relationship is what you call a similarity relations. And you see that, so if A and B are two matrices which represent T with respect to two different ordered bases, they are related by the relation A equal to C inverse, where C is such a relation. So we can say that you look at all the n by n matrices with entries from F, you say that A is related to B provided there exists an invertible matrix C such that this relation holds. This is a very crucial relation. So you see that if we define the relation between A and B, this particular relationship between A and B or if we consider this relationship between A and B, it has some speciality. So okay. So consider with entries from F. If we say that A is related to B we say that A is related to B where X is an invertible matrix C such that A equal to then it defines an equivalence relation on naturally it induces a partition. And each equivalence class consists of matrices F the same operator X, of course with respect to different bases. So that is a scenario. It actually induces a partition. Okay. So I can write here so if you go to another block in this, they are not matrices which can represent this, because once it is partitioned, you see that these are exclusive classes and this cannot represent the same linear transformation. Therefore, we found that there are several matrices which can possibly represent a linear transformation. That is the first finding. Secondly, they are all related through a similarity transformation of the type A is equal to CB C inverse, where C is invertible. Okay. Therefore, legitimately we can ask a question whether there is a simple matrix which represents it. So the question is, and operationally and more specifically, you see that diagonal matrices are easy to as regards to taking addition or multiplication or taking powers or writing down polynomials of operators, they are all very simple in this case. Therefore, we would like to see whether you can get diagonal matrix, a diagonal matrix representing T. So, we would like to know a diagonal matrix representing T. This is the question. This is the problem of diagonalization. Let us explore this. I am not going into the details of this, but we will look at the outcome of the earlier investigations of this. And then we induce an inner product on the space and see what further insight we get into this. So, this is the question of diagonalization. This is the problem of diagonalization. The answer to this is no. Not that every linear transformation can have a diagonal representation. The answer to this question is no. In fact, there are linear transformation which do not have diagonal Okay. Now, further investigation throws some more light into what kind of linear transformations have diagonal representation. Therefore, the next level of the question is this. If this is the scenario, is it possible diagonalizable, which means it has a diagonal representation. This is the central problem. Okay. Let us explore this a bit more further. It's quite easy to see what happens. So the problem is this. If I put this in detail, what you are asking is this: can you find an ordered basis for x with respect to which T is represented by a diagonal matrix? Whenever, wherever, see, this is an inverse problem. So here the problem is this. Now you want T to be represented by a diagonal matrix, if it is possible. So that's a main question. Is it possible? If so, how to get hold of this? The problem is to get hold of an appropriate ordered basis for x. So this reduces to, so that is the next level. This means whenever T is diagonalizable, how to find an ordered basis for x which the matrix T is diagonal. So that's the problem. Whenever T is diagonalizable, how to find an ordered basis for x with respect to which the matrix representative is diagonal. So this is an inverse problem. And therefore difficult. It is not directly just computing something. but going beyond that. Let us explore this, because this exploration will lead to what is called the eigenvalues and eigenvectors of the operator, and then connect everything with the so-called characteristic polynomial of T, whose roots represent the so-called eigenvalues, and the corresponding vectors give the eigenvectors, and these eigenvectors are likely to be the ordered basis that you can choose wherever it is possible. So let us work on that. It's very fascinating actually. Is the whole structurally how all these things come up. So let us explore this. Some more insight into this ordered basis. Okay. So let lambda that is along the diagonal lambda 1, lambda 2, etc., lambda n, elsewhere 0. With respect to a certain ordered basis. How to get let us explore this. Let me go back to the figures again. So what I have is this. See, this is your x. This is another copy of x. For convenience, I am separating it out. Now you see that there is a copy of fn. There is a copy of which is obtained isomorphic to x through some isomorphism. So let phi denote this isomorphism, and let us assume that you have lambda representing these are the matrix representations of x and tx with respect to, or this is equal to what is called yx. Now we are assuming that T is diagonalizable and lambda is the diagonal representation in some ordered basis. We don't know what it is. So we are trying to relate the whole thing. So let us see what happens in this. This diagram will help you to understand this problem better. The first thing that you observe is that the standard basis for Fn, the standard basis for Fn is have a role to play. So let us start with the standard basis for Fn. Where EI Eigen, okay, and this is for and delta Ij equal to 1 whenever I equal to j equal to 0 here 1 stands for the multiplicative identity element of the field, 0 stands for the additive identity element of the field. Okay, right, these are the symbols for that. In fact, when F is R, C or Q, etc., then you see that it is going to be the 0 element and the unit element 1 and the 0 element respectively. Now let us look at the status of this. Observe that or what we say is that EI is the eigenvector of lambda associated with the eigenvalue now let us recall this. Now this is just this is the problem is this: when is lambda minus this non-invertible the values of lambda for which this is non-invertible are called the eigenvalues of lambda. Just keep that in mind. We all know what it is in this case. Okay. Therefore, you see that if it is diagonalizable, then you see EIs are the eigenvectors of lambda associated with the eigenvalue lambda I. Okay, now can you go back from there? Because you see that if we observe that phi inverse of E1, phi inverse of E2 is an ordered basis of X, where phi is the isomorphism. Okay, right, with respect to which lambda is diagonal. Now we will go back to the figure and try to find out what it is. Okay, so you see that, okay, what about T of phi inverse of Ei? T of phi inverse of Ei. So you are taking here. Now you can see that this is equal to, see, yeah, this is what we want to find out. T of phi inverse of Ei is essentially now apply phi to it. If you apply phi to it, you will get Ei. Okay, right? Then see, T is essentially what? T is equal to, first apply phi, then apply lambda, then phi inverse. Okay, therefore this is equal to, so let us now consider this. So T of let's work that out. So T of phi inverse of Ei equal to T is what? Pi inverse of lambda phi which is equal to phi inverse of phi inverse is identity lambda Ei. Okay, which is equal to phi inverse of lambda I Ei. This is equal to lambda I phi inverse of Ei. Therefore, what we have is an eigenvector of T belonging to lambda I. Or you can show that both T and lambda have the same eigenvalues. One can easily see that. Eigenvalues. Okay, and lambda is a determinant, therefore it is, see, in fact I should write here same eigenvalues. Therefore you can find out the eigenvalues of T from the eigenvalues of n by n matrix. Computed by computing the which you know is a matrix. In fact, the characteristic polynomial is the characteristic polynomial. Which is an n by n matrix, and you know how to calculate this, that is this is the characteristic polynomial P lambda. And therefore the roots of this P lambda give you what are the eigenvalues. So this is an nth degree polynomial. Okay. So you see that both T and phi inverse of EI would give you the ordered basis with respect to which the T is the diagonal, T has the diagonal representation lambda. Whenever it exists, still not sure whether it exists in all cases, but wherever it is possible. Therefore, the problem is it possible? So, these are what are called eigen vectors of T. So the problem reduces to finding out what are called the eigenvectors of T. T and finding out whether this ordered basis, these eigenvectors so that is the problem. Okay, and of course you know that you don't have to work with a diagonal to start with. You see that in this context, recall that for any n by n matrix representation, T, the characteristic polynomial is the same and is hence an invariant of
characteristic polynomial. So finding out the eigenvalues of t is simple. I mean, at least theoretically, because all that you need is compute the characteristic polynomial. To compute the characteristic polynomial, what you need to do is use any matrix representation of t. That means you start with any ordered basis and then construct the corresponding matrix representation and compute the eigenvalues of or the characteristic polynomial of the matrix representing t. That is the same as the matrix, the characteristic polynomial for t. And the roots are also the eigenvalues of t. Once you get the eigenvalues, you can find out eigenvectors. So eventually what comes out is this. Eigenvectors of which spans f. If yes, then it forms a basis for x. I will say an ordered basis. It is enough to say basis. So ordering you can do. Now inducing an order on this, we can corresponding matrix representation representation this is diagonal with diagonal entries given by Eigen. So this is what you see. Okay, if T is diagonalizable, we will have sufficiently many linearly independent eigenvectors to span the space, and if that is possible, then T is diagonalizable. The situation where it doesn't happen is when you do not have sufficiently many eigenspaces for this. Okay, so I'll just conclude today's talk here, and I'll continue with this and explore this further through few more steps, and then return to what are called the analogous problem in the inner product spaces, or what happens if you have the additional structure of inner product with it, and then what comes out of it we will explore. Okay, thank you very much.